So let's talk about pitfalls of using LIME in practice. So learning goals is that you should understand why you should use it with caution and the corresponding pitfalls. So LIME is one of the best known interpreted machine learning methods, but several papers caution to be careful in practice. And there are many different kind of reasons for doing that, and we're talking about all of them now in the upcoming slides. So we're talking about sampling procedure, extrapolation, talking about the definition of locality, so it goes to sensitivity, scope of feature effects, so whether they're local or global ones, faithfulness, the surrogate model itself, and again, going back a bit to sensitivity, this is the definition of superpixels in case using image data. So let's start with the sampling part, right? So we need to sample our local neighborhood somehow, the problem is most common strategies do not count for correlation between features. So maybe we're sampling now some new data points which are fairly unlikely that we would ever observe them in practice, in the real world, right? And nevertheless, we use them to learn a local explanation model. So that could mess up actually the local explanation method and therefore your explanation in the end. So solution one could be use a local sampler directly on your version space and maybe on and making use of what is actually correlated. The problem is the derivation is particularly difficult for high-dimensional or mixed feature spaces, right? So we understand how the correlation works. It's maybe not obvious how to do that. We can also do is use the training data to fit the surrogate model. The problem is, of course, you need access to the training data in the first place. If you're doing that as a more black box explanation, it might not have that actually. And of course, it only works well when you have enough data near the point we'd like to explain. On the other hand, I would say if you don't have enough data close to the point we'd like to explain, your model is anyway not so trustworthy in the first place. So let's talk about locality. So the pitfall is that it's difficult to define locality. So how samples are actually weighted locally, which you need then to train your surrogate model. So for really choosing correct metrics, there is no automatic way. You need some kind of expertise. So we talked about an exponential kernel doing that, right? This was in that form over here. And the problem is you need then the distance measure, which could be Euclidean metric. And what you also need is the kernel width actually to say, yep, how far you should go actually. Here an example. So we have some points over here from kind of distribution here sampled and that kind of trend, right? And if you would like to explain that point or that point, and now using different kind of kernel width actually, nevertheless then with the same kind of distance measure, you see that's the different kind of sensitivity now the kernel width, right? So you could easily mess it up. The problem is if it's too small the kernel width, then it will be very, very local, maybe overfit to local noise. If you're making too large, you see, okay, now you're getting a local model which looks like that, which makes no sense at all there, right? Because then we covering again the more global trend. That means we've taken too many of our points into account. So as I said, large kernel width leads to interaction with points further away. So we have more the global trend, which is unwanted, right? We would like to have local explanations. And small kernel width leads to small neighborhoods. And then maybe we fit noise and maybe have very few data points which are really reasonable there. Solution two, use the Gower distance where no kernel width is actually needed to be specified. Problem data points far away receive a weight larger 0. The problem is that, of course, that means that we still have rather global surrogate because it's not ignoring everything from your sampled points, right? Have to be careful again with how you sample simply. So then let's talk about the next pitfall, which is local versus global features. You can see that sometimes you have features which only are important for very local effects of things and are maybe less important for the global ones, and the other way around, right? And that could simply mean that if you try now to approximate your local surrogate model and your kernel width is too large, it could happen that we still pick up more the global trends, because the global features were nevertheless more important also in your underlying model you would like to interpret. And yeah, what should happen then? Of course, you cover again local trends, which is not intended. So some features influence the global shape of the black box model simply, and that simply then overlaps with the effects of local features, which you might not really see then in your local explanations. A very famous example, if you're using something like a tree-based model, like a decision tree, you first split on the very important global features, right? The first split on variance above, you split on the most important one, so that the less important ones are closer to the leaves, but what could also mean that the local effects are more hidden towards the leaves, so that you might not really discover the local effects for some of your explanations. Here we see that as an example. So we have a binary classification model here, again, between red and blue here, an example. And we see that now we have the black and gray crosses, so that's the training data over here, right? Oops, training data. The green dot we would like to explain. You see that over here, right? The black background color, of course, gives you the decision boundaries and so on. The dark gray curve, the exact decision boundaries, and the dotted lines are now your local decision boundaries. And you see that somehow it's not a good fit over here, right? So what I would expect more or less, I don't know, would be something like that maybe. But now that's really fitting that way, because now we first split on one of the axes, and then we see that even if you change the kernel width, actually you not get a very good one. So what are the solutions to that actually? So one solution is we find closest point to X from other classes. Right? So not focusing only on our own classes over here, but saying we would like to go a bit over the decision boundary. So we're starting with that point over here. We sample, and figure on one point, which is actually having a different kind of prediction label. And then we sample around that locally again, and using that now to come up with our decision boundary, right? So that would simply prevent that we simply taking all of these, but doing that a bit more locally on the one which really matter for making our decision on whether belonging to the one class or the other class. Yes, so that could lead us then to better decision boundaries, which is that one in that case. I think it could be still even moved a bit up, but you see the trend of the red curve is now much better actually than the green and the blue one. Next one is faithfulness. So we always trade off between local fidelity and sparsity, right? So locally fidelity means we'd like to really accurately approximate our global model. But if we're going too sparse because we'd like to have better explanations or easier to understand explanations, then maybe it's not easy actually to have local fidelity anymore. So there's this trade-off, right? How complex can we go with our local surrogate models? So let's talk again about the credit data again. So, and say that the original predictions came from a random forest for one data point, and saying that belonging to class 1 was getting 40%, so it's credit score, right? And furthermore, let's say we have a linear model now with 3 selected feature, age, the account and duration. As always, we simply weight them by our model weights. And that gets us to now actually a prediction for that point of 0.283. So that's quite a bit off, right? To the 0.14, sorry. If you're now going to generalized additive model with all 9 features, which is of course much more complex, now we're getting again to much closer, right? So it's again an easier to interpret model because that's again a linear model, and the original model was random forest. But now we're using 9 features, everything is much more complex. We have now to talk about 10 weights if we're talking about the bias term in addition. It's much harder now to explain it to someone. Next pitfall is hiding the biases. So actually there was shown in 2020 that the developer could manipulate the model to hide a bias. And that's of course a problem, right? So if someone would like to deploy it and have malicious intent, for example for discrimination or so, they could do it, and I will not help you necessarily to figure that out. And here's how you can do that. So first of all, you need the classifier to determine whether that was in distribution or out of distribution data points. So if you're going for in of distribution data points, you use the original biased model. For out of distribution points produced for our local explanation, right? You sample these point of these. And that's very easy as they go out of distribution of your original distribution sampling, if you don't have access to this. And then they're using for these kind of points actually an unbiased model, right? Now you're starting to query your model. So what you're doing is actually all your these, some of these will go that way and some will maybe go that way. And of course for the unbiased model, which is the out of distribution one, there maybe go a lot of these actually in there, which then will impact also the output of the adversarial model in the same one as the other one. And then we maybe not seeing the bias anymore, right? Because that should actually not play a role because that's out of distribution. So they can hide it simply. An example could be that you, the question is whether you approve a loan or not, and you could maybe make use of gender as in our credit data set. And of course, maybe you have biased model where you make use of gender, maybe by correlated feature, maybe not intendedly directly, so maybe duration of parental leaves is for women often higher than for males, and could lead to unfair predictions. On the other hand, you also train a model on the without all these features correlated with gender, so have an unbiased model, and simply use it to hide that you're actually using for everything which is in distribution that you use actually a biased model, right? So that's a big problem. Next pitfall is robustness. And that means simply that sometimes explanations are not stable if you have small changes. Like if you remember the adversarial example, we're also saying if we slightly changing our data point, getting different kind of predictions. Now the argument is saying I changed slightly my data point I would like to explain, and I will get different kind of explanations. And that's of course a problem, right? We would expect that if I have a slight change of the data point I would like to explain, then I will get this similar explanation. That's not always the case. So if we have here a linear regression model, of course, slightly changing that one will not really change our explanation. But on that kind of surface here with a tree-based model, random forest actually in that case, slight changes could lead to complete different kind of explanations actually, if you're using now a linear surrogate model. That's of course not really intended, but that's a common pitfall. Okay, coming back to the definition of superpixels, we discussed that already a bit. So the problem is that we can have instability because of a specification of superpixels for image data. So simply, if it's making too large, maybe you're losing some fine-grained information the model makes use of, and making it too small, then it will be very, very noisy what kind of points you're actually moving then from your local explanation, right? So it will also not help you then to come up with something very good. So there's again a trade-off between these two, and it's a priori not known actually how you can do that. Even worse, that you can run an attack by simply changing superpixel as part of your intracellular attacks, because then you can get changed explanations again.